Hi everyone. Today we are going to learn about valence bond theory of coordination compounds. So we have already learned about the drawbacks of Werner's theory, and that time I mentioned to find out the hybridization, to find out the magnetic behavior, and to find out whether the complex is inner, outer, and also to figure out the geometry of the complex, we move on to another theory called as VBT, that's called as valence bond theory. So basically, valence bond theory help us to figure out, first of all, the hybridization. Based on hybridization, we can talk about the geometry, like it could be octa, tetrahedral, or square planar, right? Based on the geometry and hybridization, we also come to know about whether the complex is inner orbital complex or outer orbital complex. And very important point about this VBT is it also help us to understand the magnetic behavior in case of complexes. So when I say magnetic behavior, whether the complex is diamagnetic or paramagnetic. But how is it possible that VBT help us to figure out so many parameters of the complexes? So there is a way of figuring out all these things that I will be talking in my next video. But in this video, I would just like to share the postulates of VBT so that you understand how to apply VBT to find out, I said, point number 1, hybridization. Point number 2, geometry. Point number 3, whether the complex is inner or outer. And the last point to be mentioned is magnetic behavior. So when I talk about hybridization, we know hybridization is a process of mixing of atomic orbitals, right? So atomic orbitals of what mix over here? Without any doubt, it's the metal ion. It's the central metal ion which participates in the process of hybridization. And we already learnt in the beginning when I began the lecture series of coordination compounds that these central metal ions belong to transition series, right? That means they should have unpaired electrons in their d orbital. Now, very important point, which orbitals of these central metal ions participate in hybridization? So I'll underline here, it could be the set of n-1d, that's the penultimate d, ns and np, that's the valence shell of s orbital and valence shell of p orbital. Now, another set which could participate in the process of hybridization could be of all valence electrons, right? Like ns, np and nd orbitals. Those are all valence orbitals. But what is the difference and how do I understand which set of orbitals will participate in the process of bonding? That purely depends upon the nature of the ligands. Very important point. So based on the ligands, whether the ligand is strong field, okay, I'll write down here, whether the ligand is strong field or weak field, which I will be discussing in this video itself. So we will understand it, what exactly is meant by strong field and weak field ligand. So I repeat, based on the nature of the ligand, whether the ligand is strong or weak, the participation of atomic orbitals is taken into consideration. Fine. Now, next important thing is, once we get to know that these orbitals are hybridized, we can work over the geometry of the complex. As I mentioned before, the geometry of complex could be octahedral, tetrahedral and square planar. That depends upon the coordination number. So if it's coordination number 6, the geometry is octahedral. If it's 4, tetrahedral. Again, if it's 4, it's square planar. So here I have a table to share with you which will make the things better and clear to you. Okay, if I say coordination number is 4, I said the shape could be tetrahedral or square planar. When will it be tetrahedral, and in other condition when it will be square planar, that depends upon hybridization. So if the hybridization is sp3, it's tetrahedral, wherein if the hybridization is dsp2, it's square planar. Likewise, if your coordination number is 5, hybridization comes as to be sp3d and the shape becomes trigonal bipyramidal. Another important thing I already mentioned, that if the coordination number is 6, the shape could be octahedral in both the cases, but here the hybridization is different. It could either be sp3d2 or it could be d2sp3. If you remember, I told you through this VBT, we could also come to know whether the complex is inner orbital complex or outer orbital complex. So what exactly is meant by inner orbital? Inner orbital means when d orbital, we have to be very specific using this term inner and outer with respect to the d orbital. Okay, if n minus 1, I said if n minus 1 d orbital is participating in the hybridization, that's the penultimate, okay, shell, then it is said to be inner orbital complex. Indeed, in some other cases, as I told you, two different sets of orbitals might participate. If it's ND, that's the valence orbital participating in the hybridization. Of course, the valence orbital of central metal ion. Then the complex is said to be outer orbital complex. So here, I think this table will make the things better and clear for you. For example, if I take this hybridization sp3d2, now d is towards the extreme outer conditions, right? So that means when d is outer, which outer I mean to say, the valence shell d orbital. So therefore the complexes would be outer orbital complex, or also called as high spin complexes, wherein here you can see d is towards the inner side, right? So when d is towards the inner side, that means which d orbital of central metal ion is participate in bonding? It's penultimate shell, n minus 1, that's the penultimate shell. In that case, the complex is said to be inner orbital complex or low spin complex. This you will understand with the example which I'll be working out with you, okay? So here we go ahead. Another important thing I told you, it also help us to understand, this VBT also help us to understand the magnetic behavior of the complex. So this you already know that all diamagnetic complexes would contain all paired electrons. So all such complexes which do not contain any unpaired electrons, that means all the electrons are paired. In which orbital we are talking about? In d orbital. So d orbital could be n minus 1 d orbital, or it could be nd orbital. So if all these orbitals contain paired electrons, then it is said to be diamagnetic. Wherein if any complex contains unpaired electrons in its d orbital, again it could be penultimate d orbital or outer d orbital, then such complexes are said to be paramagnetic in nature. So based on this pairing of the electrons, or whether the electrons are not paired, that means they are unpaired, it also decides the geometry and the hybridization. But how do we decide whether the electrons will be paired or unpaired in these d orbital? Is due to the influence of ligands. Very important point, okay? So these ligands are so influential that they will cause the electrons of the central metal ion either to pair up or to be unpaired, depending upon whether the ligand is a strong field ligand or a weak field ligand, which I mentioned before here as well. So let us understand what exactly is meant by strong field and weak field ligand. Strong field ligands are all those ligands which help in the process of pairing up. So they force the electrons to pair up. Remember this. And once the electrons are paired, it also depends that what would be the hybridization, and hybridization soon depends upon the coordination number. That means how many ligands are interacting, whether the ligands are 4, 5 or 6. Now in case of weak field ligand, when we talk about, it's just the opposite of strong field. Strong field are so powerful that they force the electrons to pair up in the d orbital, whether it's penultimate d orbital or the outer d orbital. But weak field ligands are feeble, okay? They're so very feeble, they're so weak that they do not enforce pairing. So they let the electrons to remain in unpaired state. So here I mention weak field ligands are incapable of pairing, okay, or incapable of pairing up the electrons in the central metal ion. Okay, now how do I know basically what are these weak and strong field ligands in the complex? So for that we have a series over here. That's the strong field ligand and the weak field ligand. So strong field ligand, you have to memorize the ligands which are classified as strong field or either as weak field. So quickly I'll just tell you: cyanido, carbonyl, ethane 1,2 diamine, then amine, this is nitrito, and pyridine. All are strong field. So they are strong enough and they will enforce what? Pairing of electrons in d orbital, whether it could be n-1d or it could be nd. Likewise, weak field ligands are very feeble. They can't reinforce the pairing. So in such cases, the ligands are basically classified as weak field ligand. So here to mention, we don't have to categorize amine, okay? Amine is classified as strong field. Fine. So here I'm going to highlight it. Just a minute. Let me take this. Yeah. So here amine I am not highlighting because in some cases they do consider, but you can, because there's a variation in various books, so amine you can put it under strong field. So when I talk about weak field ligands, again I have a series with me which is iodido, bromido, chlorido, fluorido, then nitrato. This is nitrito and this is known as nitrato. Then of course hydroxyl group, oxalato and aqua. Okay. So all these ligands you have to memorize the series and understand whether it is strong or weak. So I think VBT is pretty clear to you. So keep watching the continuation of VBT and how to work out, I repeat again, the hybridization, the geometry, whether the complex is inner, outer, and the magnetic behavior based on the nature of ligand, whether they are strong field ligand or weak field ligand, and to find out what would be the hybridization as mentioned in this table will be discussed in next video. So keep watching and stay safe. Thank you all.